Functions are a means of representing equations in a manner that may offer us a bit more versatility in what we can do compared to if we were to just use the traditional y equals whatever the expression is going to be. With functions, we can potentially just represent whole expressions by a single phrase in the question or the working. It can also make it clearer exactly what we're going to do with the x value, or how we're going to be combining equations together. To start off with, just with some notation, you may see functions represented like this. We have like the f of x is 3x plus 4, and the g of x is x to the power 5 minus 9. So we're saying that every time you saw an f for that function, whatever was in the bracket would be the value of x in this equation here. And whenever we saw g, we're going to be working with this expression, and whatever value is in the brackets, x would have that value now. You could alternatively also see these functions represented like this, with just a letter, a colon, then the x followed by an arrow pointing towards the equation. This is the exact same thing. These mean the same, it's just a different way of displaying it on the page. You may also then just see after a comma an expression such as this. As ever with expressions in maths questions, if you have a comma and then some other like x doesn't equal or x, what we have here, that's not part of the equation itself. That's just like a little caveat or a footnote, just a mathematician acknowledging that a certain parameter for the equation, so x has to follow these rules for this to work. In this case, these three symbols here are telling you that x can be any real number. So this could be described as the domain of the function, but domain and range are terms that we're going to come to a little bit later, just to introduce the symbols for it now, just because they may appear fairly frequently if you were to now start looking at some functions questions alongside this. To more go over then the basic functions of functions as you potentially have covered in GCSE. If we were to have like the f of 2 here, per what I was saying before, this is now saying first of all, the f, it means we're going to be using this expression here, and the value of 2 in the bracket means that x now has a value of 2. So this would be the same as saying 3 times 2 plus 4, so 3 times 2 is 6, add 4 would get you a value of 10. Alternatively, we could have the overall value for the function first and not know what the x is going to be. They're going to give you some other letter for it rather than x, because x is just meant to be like a generic variable, just like in your straight line equations with y equals mx plus c, x isn't a specific thing, it can be substituted for anything. Because there is going to be a specific value that makes it equal 6 though, we'll use another letter, in this case a. If we were to start by trying to fill in the expression as we had done before though, what we'll be saying is 3a plus 4, and now we can say already that this would equal 6, because the whole function, f function of a equals 6. To rearrange, you would minus the 4 over, so you'd be left with 3a equals 2, and therefore a equals 2/3. If you then just wanted to check that answer, you could always plug it back into the original. So 3 times 2/3, well, that'll give you 2. 2 add 4, indeed, gives you that 6. We could then apply those same principles to the g function. So if we've got the g of b equals 5, then we'll say that b to the power of 5 minus 9 equals 5. Add the 9 over, so b to the power of 5 equals 14. And so b would equal the 5th root of 14, which will be approximately 1.695. Or we could have a value for the x inside the bracket first, so just say the g of 3. So you replace your x with 3, so it's 3 to the power of 5 minus 9. This would be 234. As well as using whole numbers or real numbers, we could just have algebraic expressions inside of our functions, not to then have a number at the end like we had in these couple of examples, but just to say, well, what would be the general expression for the f of x plus 1? As ever, whatever goes inside the brackets is now the value of the x here. So if we've got the f of x plus 1, we're now saying it's going to be 3 lots of x plus 1 plus 4, which if we were to just expand that would become 3x plus 3 plus 4, which would be the same as 3x plus 7. Similarly here, if we had the g of x squared, well, x now gets replaced by x squared, so x squared to the power of 5 minus 9, that would be x to the power of 10 minus 9. So these, as I say, are the more fundamental applications of your functions. But what if we now wished to combine these functions together? These we could refer to as composite functions, to have one function appearing inside of another. This you may see written as f, g, and in this case what I'll use inside the bracket, is minus 5. So when you have these composite functions, what you're going to want to do is essentially read right to left. Start with the letter that is nearest to the bracket, and then work your way leftwards. A way potentially of thinking about this is to put brackets around, in this case, the g of minus 5. So think of it as the f of g of minus 5. So if you get a value of g of minus 5, then substitute that into the f. G of minus 5 is going to be, so minus 5 to the power 5 minus 9, which is going to get you a value of minus 3,134. So to now do the f of minus 3,134, which is the same as the f of g of minus 5, that will be 3 lots of that number, then add 1 afterwards, which will get you an overall value of minus 9,398. If we were doing it the other way round, if we had wanted the g of f, and this time I'll use another example where it's just an expression of f rather than a specific expression of x rather than a specific number. Let's just say so the g of f of x over 8. So because the f is on the furthest right, we'll start with that. So the f of x over 8 would equal, so 3 lots of x over 8 plus 4, which isn't really going to simplify in any way. It would mean that most you could just get rid of the brackets and make the 3 part of the numerator here. But other than that, because we don't know what x is, we're not going to really bring it together any further. If you really wanted, you could make it a singular fraction. You could say that 4 is going to be 32 over 8. Therefore, this would be the same as 3x plus 32 all over 8 as a single fraction, but that's up to you. The main thing is, now we would be doing the g of your, I will put that as a single fraction, so your 3x plus 32 over 8, so that's what's taking the value of the x here, so we'll just have, again, that exact same fraction, the 3x plus 32 over 8 to the power of 5 minus 9. Again, there would be no obligation, if it did come down to this, to expand and simplify any further than this. It would be too ridiculous to try to get you to expand that all 5 times. You could just leave that as an expression for the composite. If there had been a value of x given, then obviously you could substitute that in and get that as a real value in your calculator, however. Alternatively, we can also have something called inverse functions. The idea of an inverse function is that is the alternate equation that would undo the usual function. So whenever you substitute an x value into the regular f, you would get an answer. The inverse f would be if you took that answer, put it in, and got back out your original number. Before, when we did the f of 2, we got 10. So for the inverse, if we put in 10, we should get 2 back out. A way of thinking about how to work out the inverse functions is to start out just with a singular x, like so, and then undo every operation from this original one, starting from the one that's furthest away from the x, and then work your way inwards. In this case, the furthest away is the plus 4 here, so the opposite of that is minus 4. Then work your way closer. The other operation is times 3. Opposite of that is divide by 3. Then if we were to do the same thing for the inverse of g, again, start with an x. The thing that is furthest away is a minus 9, so the opposite of that is plus 9. then next you have the power of 5. So the opposite of that is the fifth root. Now, this kind of method of thinking about it maybe doesn't work as well when we're going to have multiple x values in an expression. We'll give examples of that later and how we can deal with those in those instances. But if that makes sense to you, again, just what's furthest away from the x, and then just work your way inwards, doing the opposite of each one. If we wanted to double check with that example I gave before, with the inverse of f, if we put 10 in here, so 10 minus 4 is 6, and 6 divided by 3 gives us that 2 that we should have been expecting. It's at this stage that we may now wish to turn to those phrases domain and range that I mentioned before, because even though they can be talked about in relation to the regular functions, there is also a feature about them that also ties into the inverse. So I just wanted to establish those first. So with the word domain, if you see that, what that's saying is what are the x values for which the equation works. As seen before with this notation, the most functions will work for any possible value of x, as we can see here with these two first examples. There's no x value for which if you put it in there it would break the equation, right? However, if you maybe had a fraction in your function and the x was in the denominator, you can't divide by 0. Therefore, you would have to say that x cannot equal whatever would make the denominator equal 0. But it could be anything else. Alternatively, if your function had a square root with the x inside, you cannot have the square root of a negative number. So you would have to give, in this case, an inequality, because there will be a range of, or a spread of x values for which it would either guarantee that it's going to be positive or would unfortunately make it negative. So you give an inequality to either say x has to be above or below this, or x cannot be above or below this, otherwise it breaks. On the other end of things, the range is then what answers you can get from any function. Again, most functions, or many functions, will be able to give you any possible answer depending on any possible x value that you put in. But in some cases you are going to be more limited. For instance, if your expression had a square in it, you cannot have a number that has been squared being negative in and of itself. So if you had a whole expression that had been squared, you could only say then that the function has to be greater than or equal to 0, because it can't be less than 0 after that it's been squared, assuming then nothing else is done to it. As for how these then can additionally relate to the inverse functions, what we can say is that the domain of fx, just the regular function, that is the same as the range of the inverse. So, if you know the domain of the original, you automatically know the range of the inverse, or vice versa. And indeed, then the range of the regular fx will equal the domain of the inverse. So it may be that when you've worked out your inverse, it seems like you should be able to apply any x value to it. So it should have a domain for the inverse of x as any real number. However, if there was a limitation in the range of the regular fx, you have to carry that forward in what you claim the domain of the inverse to be. These then are our core concepts, whether it's taking a function and giving a value inside the brackets and then replace the x with in the equation, or getting an overall value for the function first and therefore working backwards to find what the x is, or it's creating a composite function, an inverse function, or maybe even considering what might be some limitations for the domain or range. If we're good with those, let's just see how you might get along with an example of your own. So here, these two functions we have on the top right are a little bit more complicated than what we have been looking at, but they should require just the same principles. So f of x is the square root of 9 minus 7x, and then g of x equals 3 over x cubed plus 3. So first of all, could you work out what expressions for the domain and range would be in terms of these two functions, and then could you work out what the composite function of inverse f g of x would be, and simplifying that down into its simplest form. So again, just with the domains, consider, are there any parameters that have to define the x's so that both of these equations individually work, so that they won't break? And then similarly, are there any specific inequalities or expressions of the answers you should be able to get from these? Again, think, what will you need to do to create an inverse, and how would you then produce this composite function? Pause the video, just have a go for yourself, and then press play again when you're ready to compare. So, for the domain of fx, so we're saying again, what x values will this work for? Well, per what we said before, you cannot have the square root of a negative value. So, the contents of the root here cannot be less than 0. At the minimum, they must be 0 itself. Therefore, x can be your 9 over 7, because 7 times 9 over 7 is 9. 9 times 9 is 0. And then we're saying that because we're taking away this value here, you actually want x to then be a smaller value, because you want to take away less. If you took away more than 9 over 7, that's when the subtraction would then take you into the negatives, and that would break. So x can be 9 over 7, or it can then be anything that's less than it. Because if we go into negative numbers, minus 7 times minus whatever the x value is, that brings it into positive. Definitely make sure the square root is positive. That's great. As for its range, this can actually be any real number. Because when you square root, if you must remember, you have two answers, both a positive and a negative. So, even though we obviously can't square root a negative number, you can still get a negative value afterwards. Say the contents of the root here ended up being 4. Yes, one of your answers will be 2, but also be minus 2. Again, we can also make sure that the value of the square root overall is going to be 0, because square root of 0 is 0. And then the square root of any other higher contents of the root here will account for both the positive and the negative amount of that value. So yes, it can be anything coming out of it. As for the domain of G, here we can't divide by 0, so what we can say is that x could be any real number so long as x does not equal 0. So long as you have the x doesn't equal 0, that's the main part, but then you may want to also just acknowledge that other than this, it could be any other number. Whether it's a negative or a positive, the rest of the expression would still work. As for the range, therefore, once again, we actually just end up with that being any real number, because it could be something really negative, something really positive, 0, doesn't matter, there's no limit on what we could get out of that one. So, as for then working out the composite function, we'll first of all need to determine what the inverse of f is going to be. So the inverse function of f, if we start with just our singular x and work outwards in towards this x here, the outermost operation is the square root, so the opposite of that is square. Then we have a plus 9, a positive 9, so the opposite of that will be minus 9. And thus we're left with just minus 7x. So to get x on its own, you would divide by minus 7. Therefore, to put g inside of f, as this would be suggesting, the main framework is going to be this fraction here, but instead of x, what we're going to have is this equation here. So 3 over x cubed plus 3 squared minus 9 over minus 7. Now, while technically this is correct, we are needing to get this in its simplest form. So, first of all, we are going to expand this first bracket, so because it's squared, we'll treat it like FOIL. So 3 over x cubed times 3 over x cubed, that's going to be 9 over x to the power of 6. And then 3 over x cubed times 3 is going to be 9 over x cubed, add 3 times 3 over x cubed, 9 over x cubed. So together, that's then plus 18 over x cubed, and then 3 times 3 is 9, so plus 9, minus the 9 from the outside, all over this minus 7 here. Now to try to simplify things, first of all, the minus 9 and the plus 9 are going to cancel with each other. But then if we were to want to try to bring the numerator maybe into a single fraction, we'll need them over the same denominator. So what we can do is we can times the right-hand one by x cubed, because x cubed times x cubed is x to the 6. Thus, all over x to the 6, you would have now 9 plus 18 x cubed, because whatever you've done to the denominator to make it the same, you have to do to the top, so that 18 gets times by x cubed as well. This is still all over minus 7, but when you have a fraction within a fraction, a denominator inside the numerator can just come back down into the main denominator, so we'll say that that's the same as 9 plus 18x cubed over minus 7x to the power of 6. That is your composite function here of inverse fg of x in a simplified form. If you wanted, you could factorize out a factor of 9 on the top, but you don't have to in this case. Okay, so if we're clear on that, again, how we've made an inverse, now combine them together, and just what was required of us when we were defining our domain and range, let's just have a go at one further question. So, the function f is defined by, that equivalent of fx here, 3x minus 5 over x plus 1, where x could be any real number, but it doesn't equal minus 1. And the reason for that being because if x was minus 1 on the bottom, that would make the denominator 0, can't divide by 0. So first of all, find the inverse function of f. So, this is what I was saying before about how if we have now multiple values of x in here, finding the inverse is going to be a bit more complicated. We can't just undo each operation done to the x in the original because, well, which x will we look at? So, there's a few different ways of looking at this. The way some people I've come across prefer is to, first of all, imagine it's instead just y equals that fraction. That's x plus 1, and then imagine that you've switched out the x and the y. So the x is now in front, and you've got 3y minus 5 over y plus 1. You don't have to do this step if you don't want to. Some people just find it easier to visualize this way, because what we're now going to do is rearrange to make y the subject again. Otherwise, you'd be making x the subject. So, to make y the subject, we can't make it the subject while it's in a denominator, so we have to times up by the whole denominator here, which is going to give us xy plus x for the x times y plus 1 equals 3y minus 5. Now, we'll need to bring the y's onto the same side and the non-y's onto the same side. In this case, let's say we were to move the xy over to this side and the 5 over to this side. So if it's a minus 5 here, it'll become a plus 5. So we just end up with x plus 5 equals, and now that'll be 3y minus the xy. Factorize out the y on this side, you know, y lots of 3 minus x. Therefore, we can just, to get the y on its own, divide by this bracket. We have x plus 5 over 3 minus x equals that y, or in other words, equals that inverse function there. Now that we have this, we can move on to part B. We're saying, well, the f of x is x plus a over x minus 1, given here, where a is an integer to be found. Well, if we're going to show this, this is a composite function. It just so happens that it's the same function put inside of itself. So to begin with, if we just start writing this out, except instead of x, we're going to write the entire thing again. So 3 lots of 3x minus 5 over x plus 1 minus 5 over 3x minus 5 over x plus 1 plus 1. Well, how are we going to simplify this? Well, again, we may want to expand on the top first and then try to make it a single fraction by giving it over the same denominator. So to times out here, that would become 9x minus 15. Now it's going to be over the x plus 1, but to make the 5 part of that as well, that would then become minus 5x minus 5 for 5 times x plus 1, because now putting over that x plus 1, as I say. Then this is all over on the bottom. Again, to make them the same fraction, you'd need to turn the 1 into something over x plus 1. Well, that would just be x plus 1 over x plus 1. So 3x minus 5 plus x plus 1 over x plus 1. We now have a fraction over a fraction. Because these are over the same denominators, we can basically just ignore them, leaving us just, and also again simplifying as we go now, 9x minus 5x is 4x, and minus 15 minus 5 is going to be minus 20. Then on the bottom, 3x plus x is 4x, and minus 5 plus 1 is minus 4. This you can then cancel through by a factor of 4, leaving you with just x minus 5 over x minus 1. Therefore, we can say that a is going to equal minus 5. The function g is then defined by x squared minus 3x, again, where x could be any real number. However, those real numbers have to be between 0 and 5. It can be any decimal between that. Find the value of f of g of 2, therefore. Well, if we were to work out the g of 2 first, so that's going to be 2 squared minus 3 lots of 2. 2 squared is 4, 3 times 2 is 6, so 4 minus 6 is going to equal minus 2. If we now put minus 2 into f, we would have, so 3 lots of minus 2 minus 5, and that's going to be over then the minus 2 plus 1. So on the top, 3 times minus 2 is minus 6, minus 5 is then going to bring it down to minus 11, and over the minus 2 plus 1 is minus 1, so minus 11 with minus 1, that just gives you a value for f of g of 2 of simply 11. As for the range of g, well, we're thinking what possible answers could we get from this? If it wasn't for the domain here, we could say that we could get potentially any real number. But in this case, because we are limited to x being between 0 and 5, we are now going to be artificially limited in what values we can get out of this expression. Because this is a quadratic, this is going to look something like this if we were to plot it on our graph paper. Therefore, it is going to have a minimum point. To double check also just where this graph would cut our axes, what you may wish to do is just factorize this expression here. So that would take out a common factor of x, and we'll have x minus 3. And for it to cross on the x-axis, we'll say that equals 0. Therefore, to just throw up an x-axis here, we are saying that it's going to cross the x-axis at 0 and at 3. Therefore, this minimum point is going to appear within the range of 0 to 5. Therefore, we're going to want to work out what that minimum value is going to be. We could either do this by differentiating the expression to get 2x minus 3 and solve for that x value and then plug that back in, or we can complete the square. If we're going to complete the square, what we would need to do is, with a bracket, get a single x and then do half of this coefficient here, so minus 3 over 2 squared, following which we would then minus 3 over 2 squared, because if we were to expand this, you'd have x squared and then minus 3 over 2x minus 3 over 2x, which gives you minus 3x, but then an extra 3 over 2 times 3 over 2, which we don't want because there's no number at the end, so we just want to take that away at the end again. So here, completed square form would be for your 3 over 2 squared minus 9 over 4. If we're looking then for the minimum value that this can take, well, the smallest value that the square bracket can take is 0, because if the contents came out to a negative thing, by squaring they become positive again. Positive also obviously becomes positive, but 0 squared stays 0. So if this then is 0, the minimum is going to be minus 9 over 4. That is the lowest possible value that our g of x could become. Then, as for the greatest, obviously you can see here our vague sketch, 5 will be over here. So the height of the graph at 5 is going to be greater than the height at 0 or any other point in between. So to get up this higher end, we're just going to substitute 5 into here. So 5 squared is 25, minus 3 times 5 is 15. So 25 minus 15, we have an upper value for our range of 10. The answers, given the restrictions of the domain, will lie only between these two here. And then finally, explain why the function g does not have an inverse. What we're going to say is that it's not a one-to-one function. But what does that mean? Well, when we are trying to get an inverse function, if we were to plot it on here, we're saying that if you had a certain a y value, you could go along to the curve and then get a point on the x-axis, and thus you would return back to the value you had before. Like in the first example, we put in x is 2 and got out 10, so when we then put 10 into the inverse, we got back our 2. The problem is here, if we say look at our sketch, let's say that we had a given x value here. Now that is going to lead to this y or g of x value here. But if we'd started with this g of x value and we went across to the curve, we could read up at this x value certainly, but we could also go along and read off this x value here. You would have two answers for the same input to the inverse function. And that's not supposed to happen. You can only have an inverse if a single input gives a single output. It's not meant to be a one-to-many function. So, if it's something like a square or a higher power, where any given y value has multiple x values that give it, it will not have an inverse because it's not a one-to-one function.